Okay, so here's the physics lecture. So some of this is going to be review, just kind of setting up what we're going to talk about. So we talked about last time about how moving a conductive material in the presence of a magnetic field will create a induced voltage across the tips of this conductor. We talked about an airplane wing moving in the presence of the Earth's magnetic field. And this happens because the electrons, the free electrons, really all of the electrons, but especially the free electrons, will experience a force which is equal to the charge of an electron times the velocity, which is the speed of the conductor, and the magnetic field strength. And if the electrons are moving this direction, well, if the positive charges are moving this way and the magnetic field is into the board, the positive charges will be pushed this way and the negative charges will be pushed that way, and you get this voltage that's created across there. Nothing. And what will happen is, the force will cause this to occur, and then you'll end up with an electric field which is wanting to pull them together, and the magnetic field which is wanting to push them apart, and you reach kind of an equilibrium situation, and then nothing really changes. Now, if you stop this thing moving, then the electric field would cause the charges to come together again, and then if you start moving, they separate again. But if you were moving at a constant velocity, you would just have the charges separated on either side of this conductor. Okay. Now, if you connect this conductor to a rail, and then the rail ends are connected by a wire which has a resistance, what happens is this voltage, instead of just sitting there and not doing anything, is going to cause the current to flow around the loop. And you can kind of tell from this, if I have a positive charge on this side, negative charge on this side, the positive charge, the positive voltage here is going to push the current around through the resistor to the other side. Now, you can also look at it from a Lenz's law perspective. So how does that work? Well, you've got this magnetic field, you've got a loop, which is made up of the moving conductor, the two stationary rails, and the resistor that's connecting the two rails. And so as you pull this thing to the right, you're going to be increasing the area. You're going to be increasing the flux. So the magnetic field strength stays the same, but because the area is increasing, the flux is getting larger. So to maintain the flux before we made the change, we want to have the current flowing around the loop so that we try to reduce the flux in the system, because we're going to be increasing because of the higher area. So if we want to keep it at the same level, we have to decrease it through some other means, which means to lower the magnetic field strength. So what we need to, if the magnetic field is pointing in towards the board, we want to create a current which will cause a magnetic field going out to compensate for that. So if we think about putting our thumb in the direction of the current going from here up this way, we'll curl our hands around the bar and we'll point outward, so that you can think of the direction of the current either from the induced voltage across this conductor, or think about it from Lenz's law perspective. So let's just read this. Assume the moving bar has zero resistance. So this has zero resistance. And also the rails have zero resistance. It says, as the bar is pulled to the right with a given velocity, under the influence of the force, or applying this force, the free charges experience a magnetic force along the bar of the magnet. This force sets up an induced current because the charges are free to move in the closed path. So that's the same scenario here, except now the charges can move around the loop. Yeah, I guess that doesn't explain which direction the current goes, but that's how it works. Now, let's read it. The changing magnetic flux through the loop and the corresponding induced EMF in the bar result in a change in the area of the loop. Okay, so we're increasing the area of the loop. The induced motional EMF acts like a battery in the circuit. So what they're doing is they're replacing this bar, which acts like a battery, with a battery, just to kind of think about what's going on here. And that battery has a value. So what they're doing here is just kind of saying, battery allows you to increase the electromotive force, increase the voltage across the battery, but you can also have the same kind of effect by this moving conductor. And then if you look at using Ohm's law, you can see that the current that's induced around the circuit is equal to the voltage, the EMF, divided by the resistance, where the EMF is this product of the magnetic field strength times the length of the moving conductive element and the velocity. Now here's kind of explaining Lenz's law to explain the direction of the current as well. As the bar moves to the right this way, the magnetic flux through the circuit increases because the area is increasing. So here's the area. As we move this to the right, these areas increasing. The induced current must be in a direction such that it opposes the change in the external magnetic flux. So as I said, if you're increasing the flux by increasing the area, you have to decrease the flux by decreasing the magnetic field. And you can do that by having current flow this counterclockwise direction. We'll talk about it in the lab, try to do that. So the flux due to the external field is increasing into the page. So the flux due to the induced current must be out of the page. That's what we're saying. So the current going this way causes a flux out of the page, which counteracts the flux going into the page. Okay. Now you can also look at the Lenz's law from a conservation of energy standpoint. So let's just walk through this, talk through it. So it says, assuming the bar is moving to the right, so we're pulling on it, assume the induced current is clockwise. So we're actually assuming it's yeah, okay. So it's actually going to be going the other way, but they're kind of using a counter argument. Assuming that the current flows clockwise, the magnetic force on the bar would be to the right. Oh, actually they're moving, assume the bar is moving to the right. Just looking at this velocity, I'm not sure why. I think this goes to the previous problem. If you push it the other way, the current would switch the other way around. Okay, I think this is just another way of explaining it. Assume the bar is moving to the right. Assume the induced current is clockwise. The magnetic force on the bar would be to the right. The force would cause an acceleration and the velocity would increase. This would cause the flux to increase and the current to increase and the velocity increase. This would violate conservation of energy, so therefore the current must be the other direction. Yeah, it's kind of like you can't create energy. And so what they're saying here, if we go back to this one where they're pulling to the right, so they're saying let's pull to the right, but assume the current goes clockwise instead of counterclockwise. Well, what that current would do is it would create a magnetic field which would cause it to be pushed to the right even more, and that would sort of be self-generating, and then you would just continue to accelerate because of that, and we know that can't happen. So we'll look at this in class. We talked about it. This is looking at Lenz's law using a magnet where the magnetic flux changes by moving the magnet in and out of this coil, and that changes the flux. So in the previous example with motional EMF, we're changing the flux by moving a conductor or by increasing the area of the loop. Here we're keeping the area of the loop the same, and we're changing the flux because the magnetic field strength is closer to the poles of the magnet than it is away from the magnet. Okay, so we'll talk about that. Yeah, skip over the things. Okay. So another thing you can do, we've alluded to this in class as well, is using Faraday's law, that if you can change the area of the loop, then you can induce a voltage, and that induced voltage can then create a current in the loop made out of conductive material, and that's how a generator works. So let's look at this. This is an AC generator, so let's talk about the basic operation. It's kind of like a DC motor, except instead of having the commutator where you have split rings, you actually have two rings that are connected to the external circuit through brushes. So as this loop rotates in the presence of this magnetic field, we're changing the area that the magnetic flux goes through. The flux is going from the North Pole to the South Pole. So as we change the flux by changing the area, we're inducing an EMF in the loop. That induced EMF is like a battery, but it's not a constant battery. It's varying with time because the area is varying with time. And that EMF induces then a current in the external circuit. So this is the external circuit. So you have the loops connected through these rings to the brushes. That transfers the current through some external circuit, which they're showing as being a light bulb in this case. And so it says the ends of the loop are connected to the slip rings, that rotate with the loop, and then the slip rings are connected through brushes. And the shape of the voltage as a function of time looks like this. It's a sinusoidal result. You generate the maximum EMF when you're changing the area most rapidly, and where you're changing the so as you go through one full cycle or loop of the rotation of the loop, you're going to go through one full cycle of the induced voltage, and it's going to have a positive voltage and it's going to have a negative voltage, and it takes on a form like this. So the voltage is equal to 2 times the strength of the magnetic field, which is due to the external magnets, times the what the heck is that? I think this must be a velocity. The velocity of the horizontal part of the loop times the length of the loop, and it's if the loop rotates with a constant angular speed, omega, in radians per second, and has n turns, then the external voltage, the induced voltage, is the number of turns times the strength of the magnetic field times the area of the loop times the rotational speed of the loop times the sine of omega t. So omega is how fast this thing's being rotated. So the rotational speed affects the frequency at which you generate the voltage, but it also affects the voltage. The faster you spin it, the higher the voltage. The more turns you have, the higher the voltage. The stronger the magnetic field, the higher the voltage. And the maximum voltage occurs when the loop is parallel to the field. What does that mean? Well, if you see the loop over here, when it's aligned so that it's parallel instead of perpendicular, parallel, that gives you the maximum voltage because that gives you the maximum change in the area, the change in the area through which the flux goes. And when it's vertical, when this loop would be vertical, is when you would get 0 voltage. And as it goes through from one orientation through vertical to the other orientation is when you go from positive to negative, negative to positive. So if you have a power plant that's 30,000 volts, this kind of gives you an idea of the parameters in terms of designing the generator. You have to spin it fast enough, but also that's going to affect the frequency at which it oscillates back and forth. How many loops you have, strength and magnetic field, those kinds of things. So here is a little bit closer detail of the generator. So it says the magnetic forces on the charges in the wires A, B, and CD. So this is A, B, and CD is perpendicular to the length of the wires. So those forces go this way. And so that doesn't generate any power. The actual voltage is generated in the wires BC and AD. It's kind of like in the motor situation. These wires, the horizontal wires here, were the ones that generated the torque. And as a consequence, the same thing applies for generators. It's these horizontal wires that generate the EMF. The EMF produced in each of these wires, so the induced voltage across this part and across this part, is equal to B, the magnetic field strength, times the length of these two wires, times the velocity of the wires, times the sine of theta, where theta is the angle between the velocity vector. So you can think of this thing rotating. You've got this tangential velocity of this loop. So go back to rotational stuff. You've got this, here's the center of rotation. You've got a distance a over 2 as this thing rotates. And so the velocity is going to be proportional to the rotational speed, omega, and the distance. And we're looking at the angle. And so to get the maximum force on the electrons, which are going to be pushing it this way or going to be pushing it that way in the circuit, is when the magnetic field and the velocity vector are perpendicular to each other, which happens right here. So when this vector is moving up like that, it's perpendicular to the magnetic field vector, and hence you get the maximum current, which is going to be perpendicular to both of them. Now when the velocity is going this way, you can see the velocity is in the same direction as the magnetic field, and you get zero force, and that's why you also get zero voltage. So you can look at it from a number of different perspectives. Now for a DC generator, you basically use the same configuration, but instead of having the slip rings, which are continuous around the entire rotation, you have this commutator, the same kind of thing you had with a DC motor. And what the commutator does is it makes it so instead of the voltage going up to positive and then going through 0 and negative, it makes it so that it's always positive. Now this is not DC, so what you would ultimately have to do is put some kind of a capacitor in there, and a capacitor would even out this. It would flatten out the voltage. It's like you're pushing somebody on a swing and you're always pushing in the same direction, kind of thing. So you can kind of think of you pushing it as this, but the inertia of the person is going to keep them moving. And we've talked about motors. Motors are just the opposite of generators. So you can use a motor as a generator as a motor. That's the whole idea about electric cars. You can use the same thing to generate electricity. So when you slow the car down and you recoup that energy, you use it as a generator, which generates current, which charges your battery. Then when you're speeding up, you take the energy out of the battery and run it as a motor. And because they're the same basic device, except depending upon whether you put energy in or getting energy out, it makes it so you don't have to have two separate devices. Most of the places before electric cars and things like that, you typically used them as one or the other. You had a a generator at a power plant, you had a motor to run something, but nowadays you are using them kind of in both directions. Now there is something we'll talk about in the lab, is that if you have a motor spinning and you're running it as a motor, but then you turn off the power, what happens is then the motor becomes a generator, and you have to protect against that, because what will happen is the current will be flowing one direction as a motor, and then once it starts acting as a generator, the current flows in the other direction. And instead of supplying power from your device, you're putting power into your device, and you can damage stuff that way. Okay, we talked about this the other day too, and it has to do with that fact that, well, it's kind of the same factor, but when you have a motor sitting still, you turn on the power, and you have a battery or external power source, and you run through the motor. And initially, the motor is stationary. It's just a bunch of wire that you get a current flowing through a loop that creates a force, gives you a torque. The motor starts to spin. It spins faster and faster and faster. And there's a self-compensating situation where the motor, as it spins, is also generating voltage as a generator, and that generator develops a voltage opposite the direction that you're applying it with the battery. And so you only have a net amount of voltage that's available to push the current through the motor. And you'll reach some place where the current through the motor is just providing enough torque to keep the motor running and overcoming friction, but it doesn't have any additional current to give you torque to make it move any faster. So you kind of reach this steady state condition. I don't know if I have a curve here showing this. I think I showed you the curve the other day. So I'll just draw it out for you. If you have a motor and you have some kind of input voltage, so that's your supply voltage. We'll call it V sub I, and we'll draw a horizontal line. So let's say you have a 5-volt battery and you hook it up to the motor, and this is speed. So at 0 speed, you're going to have the full voltage of the battery, or whatever it is, to provide current to the motor. Now once the motor starts to spin, the motor starts to generate a back voltage that reduces the net. So this difference is the voltage. Let's call it V star, okay? And V star is the net voltage available to push current through the motor. So initially we have a lot of current. We have a lot of voltage to push current through the motor. But as it starts to spin, you get less and less and less. And then you get to some point, some speed here, which is kind of your equilibrium speed, your max speed, where the amount of voltage that's available to push current through the motor is just enough to provide the torque, which is going to balance the friction. As you go to higher and higher speed, the friction increases. At low speeds, the friction's low because it's not spinning as fast. Plus, you have more available voltage to drive current through it. But then you end up getting to this limiting factor. But even, at some point, even if you didn't have friction, you get to a point where these things would actually be equal to each other. So that's why simple motors don't have a speed control, because they're going to come to some natural speed limitation. Now if you apply load to that motor, it's going to slow down because you need more voltage, current, hence current through the motor, to create the torque to keep the motor running. Okay, so that's in the case of where you have a coil of wire that's spinning and creating a changing magnetic flux, because you're changing the area of the loop, which is used to define the magnetic flux. Now, you have these situations where you have something that's not moving. You do have a coil, and it also has a similar kind of self-compensating situation. So let's talk about that. It's called self-inductance. And self-inductance occurs when the changing flux through a circuit arises from the circuit itself. As the current increases, the magnetic flux through the loop due to this current also increases. The increasing flux induces an EMF that opposes the change in the magnetic flux. So you're getting a magnetic flux that is induced from the changing current, and that changing magnetic flux results in a voltage which fights against the current that it produces an EMF in the opposite direction, which has a tendency to slow the current down. As the magnitude of the current increases, the rate of increase lessens and the induced EMF decreases. So what they're saying here is, because of this induced EMF, it decreases the available EMF, just like in the motor, and it causes the current rate of increase to decrease. So the whole idea of the self-inductance is it produces an EMF which sort of limits how quickly the current can change through a loop or through a circuit. So before we talk about that, I'm going to kind of go through some scenarios here. You know, we talked about capacitors, and we said if we hook up a capacitor to a battery, what would theoretically happen is, as soon as you close the switch, the capacitor would almost instantaneously become charged, because there's nothing to limit how quickly the charge gets redistributed around here. So it's the second kind of circuit we looked at was an RC circuit. So we had a resistor. So what happened in this case is we had this, again, a switch. So initially the capacitor is not charged. So we close the switch, but instead of the charge instantaneously charging the capacitor, it's going to be limited by this resistor through Ohm's law. So what happens is, initially when you close the switch, you get the current through the resistor is determined by Ohm's law. Current is equal to voltage divided by the resistance. So initially you get all the voltage drop across the resistor, and the amount of current flowing through the resistor is the maximum to start with. But once it starts charging the capacitor up, the voltage across the resistor becomes less and the current becomes less, and so this kind of slows down how quickly the capacitor can be charged. But if I looked at current as a function of time, what I would see is that before the switch is closed, the current's zero. When I close the switch, the current goes from 0 to some value instantaneously, and then the current dips off as the capacitor gets charged. That was the voltage, or the current. The current in this circuit as a function of time is equal to some maximum current times e to the minus kt, where k is equal to 1 over RC, the time constant. Now, nature does not like discontinuities, meaning you go from one value to another value almost instantaneously. So we're missing one situation. In any circuit, you can design into the circuit, you can design an inductor into the circuit, or just a wire is the simplest kind of wire is the simplest kind of inductor, because even around a wire we create a magnetic field. It's just an inductor is like a solenoid, and it just gives you more, and it gives you more inductance, so it causes this phenomenon to happen to a more significant degree, but just a wire itself will act as an inductor. So what happens here is that the inductor makes it so that you can't go from zero current to some current instantaneously. So we'll come back to that later, but right now I'm just trying to build up to it. Here, the simplest case, which is not reality, is you just have a battery and a capacitor. The capacitor fills instantaneously. Again, that instantaneous is a discontinuity, doesn't like that. So if you put a resistor in there, the capacitor doesn't fill instantaneously. It takes a while for the charge to go through the circuit, but we still have an instantaneous change from zero current to some current through the circuit. So that's not realistic either. So you have this other element to consider, this self-inductance. So the self-inductance, self-induced EMF associated with this coil must be proportional to the time rate of change of current. Why? Because if you remember, in the magnetic field inside of a coil is equal to the number of turns per length times the current times the what else is it? Times the, there's another thing. It's mu zero, that constant, mu zero, the magnetic constant. So this is built into the geometry of the coil. So to get a rate of change of magnetic field, you have to have time rate of change in the current. So that's how you get a changing magnetic field, is by having a changing current. And so this induced EMF in the coil has to be proportional, so we have this proportionality constant times the rate of change of the current with respect to time. And you probably can imagine that that L value has some relationship to the geometry and the number of wraps in your solenoid, and also this constant. It's not a, this is the rate of change this is the induced EMF. This is just the rate of change of the magnetic field, so it involves some other things as well. Now this proportionality constant is called the inductance. Just like a capacitor has a capacitance, an inductor or a coil has an inductance. And the negative sign indicates that a changing current induces an EMF in the opposition to that change. So what that's saying is, if you're come down to this inductor, if you're increasing the current through this inductor, so the current's going this way and it's going from zero to some higher value, as that rate of change is positive, that creates a induced EMF in the opposite direction. So it kind of acts, it almost acts like a resistor in some ways. It resists the flow of current through here, but it's not the resistance to the flow of current is based on the rate of change of the current, not proportional to the current like a resistor is. So as the current's increasing, you have a voltage drop across the inductor. So in the case of if the magnetic field strength is increasing because the current is increasing, then you have a situation like that. So if this is greater than 0, then you have a voltage drop. If you had a going the other direction, if the current was decreasing so that the magnetic field was decreasing, then the voltage changes across the inductor. And it doesn't matter upon which direction the current's flowing, it depends upon which direction, whether the current's increasing or decreasing, which relates to the changing magnetic field. And so the inductance of a coil, which is the usual element that we use as inductors because it gives us the maximum value of inductance, depends upon the geometry of the coil. The units for inductance, this L, you can get by just looking at the units for the other terms. So EMF is in volts, current is in amps, time is in seconds. So you get volts, seconds per amp. Volts, seconds per amp. We call that a Henry. So the units of inductance are henries, the units of capacitance are farads, the units of resistance are ohms. And if you take this expression and relate the fact that the rate of change in current can be related to the rate of change in magnetic field, you find out that the inductance is the number of turns times the rate of change of magnetic flux with respect to the change in the current. And these are both rates of change, so you can cancel out the dt parts and you get that the inductance is the number of turns times the magnetic flux divided by the current. So this doesn't actually tell us yet how you would get the inductance from the geometry of the element. And this guy, Joseph Henry, was kind of the one that did the pioneering work. So what did he do? He was the first to produce an electric current with a magnetic field. He improved the design of electromagnets and constructions of motors, and he discovered this whole concept of self-inductance. So let's look at the inductor in a circuit, just like we looked at the capacitors and resistors in the circuit. So the inductance can be interpreted as a measure of the opposition to the rate of change in the current. So let's go back here. The inductance can be represented by interpreted as opposition to the rate of change in current, because the rate of change in current causes an EMF, which results in a lower EMF available to drive electrons through the circuit, and hence it opposes current flowing through the system. Okay. Remember, the resistance R is a measure of opposition to current, whereas inductance is a measure of opposition to rate of change of current. As a circuit is completed, the current begins to increase, but the inductor produces an EMF that opposes the increasing current. So what the inductor does is it prevents you going back to my previous discussion. When I didn't have an inductor in the circuit, I went from zero current to the maximum current instantaneously. What the inductor does is it produces a back EMF that makes it so you can't go from zero current to full current, because the faster you go, the higher the EMF, and if the change in current can only be so high because it would produce an EMF bigger than the EMF that's driving the circuit. Therefore, the current doesn't change from zero to its maximum instantaneously. It's limited because of this inductance. And even with a circuit that doesn't have a coil, the wire itself acts as an inductor, and that things still change pretty quickly, but they never change instantaneously. So what we have is this RL circuit instead of an RC circuit. So what happens is, in this case, we have that in an RC circuit, the current goes to a maximum initially. In a RL circuit, what happens is the equilibrium condition is not the capacitor is fully charged. We reach a current and the inductor reaches a steady state situation, and therefore there's no change in current and the inductor just acts as a wire. The only time the inductor works as something other than the wire is when you're changing from one current level to another. So when the current reaches its maximum value, it's constant and there's no rate of change, and therefore there's no back EMF. So this thing only gets involved at the beginning when you go from zero current to the maximum current. Once you get to the maximum current, it's just kind of there. So when the current reaches its maximum, the rate of change and the back EMF are zero. And this also has a time constant as well, which is R times L, not R times C like it was for RC circuits. And just like for RC circuits, though, when the product of R and L equals the time, you've reached 63% of the final current in the circuit. For an RC circuit, it was 63% of the final voltage in the capacitor. Actually, the time constant is not R times L, it's L over R. And the current at any time in the circuit is equal to the applied voltage from the battery, which is typically constant, divided by the resistance of the resistor times 1 minus e to the minus t over the time constant. So when t becomes large, this term becomes e to the minus infinity, which is 0, and you get the current is just the current through the resistor using Ohm's law. So as t goes to infinity, it just becomes Ohm's law. But during the initial phase, the current goes from 0. If you put in t equals 0, you'll get 1 minus e to the 0. E to the 0 is 1, so you get 1 minus 1. The current starts off at 0, and it goes through. And if you plot, that might be on the next page. No, it isn't. So let me plot what this thing looks like. So if I wanted to plot the current, and I'm going to use a small case I, current is a function of time, what you'd have is the maximum current, which happens after a period of time. The current starts at 0 instead of going up to this maximum immediately, like with RC circuits. What happens is that it has this shape. It looks just kind of like the voltage in a capacitor, and then it comes up here finally, asymptotes. And the slope of this line, di dt, so going from 0 to some value, this initial slope is related to the EMF. In that case, the EMF that's applied by the battery, this is the battery voltage, is going, so I'll say EMF by the battery is going to be equal to the EMF generated in the inductor, which is going to be equal to, I guess it's probably negative and negative. So you get negative and negative L times di dt. So this slope of this line times the inductance at t equals 0 induces a voltage in the coil which is exactly equal to the voltage that is provided by the battery. And just like you can store energy in an electric field in a capacitor, you can store energy in the magnetic field of an inductor. Now, if you remember from capacitance, the potential energy of the capacitor was equal to 1/2 the capacitance times the voltage squared. For an inductor, the energy, the potential energy stored in an inductor is equal to 1/2 the inductance times the current squared. And there's chapter 20 homework, which you've got the handout. So let's kind of go back here, talk about what do we cover in chapter 20 now. And I'm just going to kind of go through this 5-minute review. So the first thing is this guy Faraday did his experiments, which showed a changing magnetic flux resulted in a induced voltage and hence a current in a circuit. And he came up with this law, Faraday's law, somewhere along here. Faraday's law. It said the induced voltage is equal to negative the number of turns times the rate of change of magnetic flux with respect to time. The magnetic flux is a product of the magnetic field. Here's magnetic flux, magnetic field times the area. If it's perpendicular, if it's not perpendicular, then it depends upon the angle between the magnetic field and the area. So we've talked about ways to change the flux. You can change the magnetic field, you can change the area, you can change the orientation of the loop. You can use Lenz's law to figure out which way current flows around a loop, current loop, and it opposes the current caused by the induced EMF travels in the direction that creates a magnetic field with flux opposing the change in the original flux through the circuit. So that's Lenz's law. We'll talk about those some other time. There is this motional EMF as well as the EMF associated with moving a conductor in a magnetic field. You can use Lenz's law. Here you would use the force on a moving charged particle to figure out which direction the charges go in the conductor. Think about an airplane wing. Then you have this motional EMF, which is the same kind of deal, except you connect the two parts of the moving conductor to a circuit, and that generates a current that flows in this loop, and the direction of the current, it can be determined using Lenz's law as well, but in this case the flux is changing because the area that the magnetic field is flowing through for this loop is getting larger or smaller. And you can show that Lenz's law is actually just a way of looking at conservation of energy. Here you can see the case where you can change the flux by moving a bar magnet in and out of a coil. Now a generator, AC generator, is just a motor being same configuration, but it's being spinned. And what you do is you have a loop of wire which is rotating in the presence of a magnetic field. It generates an EMF around the loop, which then pushes current through the circuit. And you end up with a sinusoidal looking output because of how the area changes of the loop changes with respect to time. If you put this split ring, then you can create voltage that's in one direction. And then we talked about back EMF, and we talked about self-inductance. So that is chapter 20. We're going to move into chapter 21. So I'm going to pause for just a second until I get my stuff. Okay, so chapter 21, which is the last of the electromagnetism chapters. We're going to look at more complex alternating current circuits. So we've looked at RC circuits, which was for DC. We've looked at RL circuits, which were for basically the same kind of situation. What we're going to do is expand this to having resistors, capacitors, and inductors. in the same circuit. And that can get fairly complicated. Also, if you take an alternating current and create an alternating voltage in a conductor, you can create electromagnetic waves, which have applicability for radio, microwave, light, all kinds of situations. So let's talk about AC circuits first. We'll spend about 10 minutes on this. So an AC circuit consists of a combination of circuit elements, meaning resistors, capacitors, and inductors, and some source of AC power. So instead of having 0 or 5 volts, we're going to have a voltage that varies between 0 and some maximum, and then back through 0 to some minimum, like we just saw in the AC generator. And the output of the generator is sinusoidal, and it has the form of the following form. So the voltage, the change in voltage, which is the EMF, is going to be some maximum voltage change times the sine of 2 pi t. Well, yeah, 2 pi. So this just shows you that it's sinusoidal. Now, in the reality, it's actually equal to delta V max times the sine of 2 pi f t. Okay, so f is the frequency that it oscillates at, and t is the time. And the 2 pi is in there so that you can get the period to work out correctly. If you remember back from pre-calculus, the period of a sine function is equal to 2 pi divided by this thing, the number in front of that. So you can see that cancels out, and you get periods equal to 1 over the frequency. So it takes on this form. The delta V is the instantaneous velocity, which varies sinusoidally between the maximum voltage and the minimum voltage. And the frequency F is the voltage at which it changes. So apparently I just left that out of there. I was wondering why it wasn't there. Now, what we're going to do is we're going to look at each one of the circuit elements individually and see how they react to a sinusoidal input voltage. For a DC circuit, or just, for a DC circuit, we used Ohm's law, and we do the same thing for an AC circuit. So what we see over here is a graph of two things. We have the current through the resistor and the voltage applied across the resistor. And these are in sync. So if you have 0 voltage across the resistor, you have 0 current. If you have the maximum voltage across the resistor, you get the maximum current. If you go back to 0, again, if the voltage goes back to 0, the current's 0. So the current and the voltage are always what we would call in phase. They happen at the same time. The maximum voltage across the resistor is when the maximum current happens, when you have maximum voltage. Now, what happens with well, let's look at this and other things about resistors and AC circuits. The direction of the current has no effect on the behavior of the resistor. Okay, we said it didn't matter which direction you put a resistor in, it's going to behave the same. So whether it's moving from left to right or right to left, it still behaves the same. The rate at which electrical energy is dissipated in the circuit is given by P is equal to I squared R. And we've talked about that before. In this case, this is the instantaneous power. So the instantaneous power is the instantaneous current squared times the resistance of the element, which is a constant value. And this power is just dissipated in terms of heat. And the maximum heat occurs when you have the maximum current. But we'll find out later that the actual power dissipated in a resistive element is not just I max squared over R. You have to take into account the sinusoidal nature of the current varying. And the maximum current occurs for a small amount of time. or actually the maximum current happens instantaneously. You know, it's not like you stay at the maximum current for a certain period of time. You just go through it and then come back down again. So things are constantly changing. We'll talk about that later. That's about RMS voltages and stuff like that. So we'll skip all over that stuff. Let's talk about capacitors in the circuits. So the thing about a capacitor is you've got to have charge on the capacitor for it to have voltage. So if you have an AC circuit, so you've got a capacitor that's initially uncharged, and you have this source which is oscillating. If there's no current flowing through here, there's no way to charge the capacitor. So it takes time to charge the capacitor. So the current starts out at a large value and charges the plates of the capacitor. There's initially no resistance to hinder the flow of the current while the plates are not charged. So when this is uncharged, you just push the current into the plate, but it doesn't instantaneously charge the capacitor. It takes a while, still takes a while to charge the capacitor. And it says as the charge on the plate increases, the voltage across the plate increases, and the current flowing through the circuit decreases. So when you have maximum current flowing through the circuit is not when you have the maximum voltage across the capacitor. It takes time for it to fill up. But by the time you get this thing to be filling up, then you're decreasing the current because it's an oscillating current. So let's assume that it starts out maximum and then it goes down through zero, minimum, back up here. So what it's saying is we start off, we're pushing the current through into the capacitor. But by the time we get to zero, we're having the current going the opposite way. We're actually emptying the capacitor. So if we look at the relationship between the voltage across the capacitor and the current flowing into the capacitor, it's not in sync. They're not at the same time. So we're saying that initially the capacitor is uncharged. We start flowing current into the capacitor. As current flows into it, it gets charged to a higher value. But when the current goes to zero, then it can't be charging the capacitor anymore because now the current's going the opposite way. So it starts to discharge the capacitor because the current's being pulled out. And when you get down to the opposite end, you've pulled all the current, all the charge out of the capacitor, and the voltage is now zero across the capacitor. Now we still have negative current, but it's now decreasing. The current value is getting less, so it's pulling out, it's actually charging the capacitor the other direction. So you fully charge the capacitor the other way. So you go from this situation where you charge this direction, which would be right here. So that's when it's fully charged. Then you would have some intermediate part where you've got the same charge, that would be here. And then since the current's flowing the opposite direction, it becomes fully charged in the other direction at this point. Then you start pulling the current the opposite direction. So you're pushing current in, pulling current out. And what you find out is that the maximum voltage is at a different time than the maximum current. And you can see these are 1/4 period apart. So they're, well, we would say they're out of phase 90 degrees. Or in this case, the voltage across the capacitor lags behind the current by 90 degrees. So the maximum voltage is 90 degrees or 1/4 period out of phase compared to the maximum current. So that's what happens with capacitors. Now for inductors, we'll come back to these things. I'm just trying to kind of lay out the thing. Now, inductors have the exact opposite behavior. The current, or the voltage across the inductor is maximum when the rate of change of current is the largest. So if you have a sinusoidal current applied to the inductor, the maximum voltage occurs when you have the maximum positive slope, and the minimum occurs when you have the minimum slope, and the when you have no change in current, which is at the peaks, you have zero voltage across the inductor. So in this case, the maximum voltage for a capacitor, the maximum current was here and the maximum voltage was there. For an inductor, the maximum voltage, the current is here and the maximum voltage is there. So it's moved opposite directions. You know, capacitance should go that way, inductance should go that way. So in this case, they say the voltage across the inductor leads the current. For the conductor, the current lagged, the voltage lagged the current. Whereas for the resistance, it's in phase. It happens at exactly the same time. So this behavior of the three different elements, the resistor is in phase with the current. The capacitor lags the current by 90 degrees. And the inductor leads the current by 90 degrees. You have to take into account that situation when you have AC circuits and you have both. You have resistors, capacitors, and inductors. Mathematically, it's fairly complicated, but there is a method that we'll teach you how to use, which is called reactance. You've got a reactance for a resistor, you've got a reactance for a capacitor, you've got a reactor for an inductor, inductive reactance, you've got capacitive reactance, you've got resistance. And you can and these values are dependent upon not only on the capacitance and the inductance, but also on the frequency that the circuit is oscillating at. And it comes out to kind of be like Ohm's law in evaluating these circuits, but instead of using resistance, voltage, and current, you use reactance, voltage, and current. So that is for another time, probably next Friday after we do our lab on Wednesday.